Hey everyone and welcome back to PrepFusion. I am Anish and today we'll start the lecture 4C of this electrostatics chapter. So up until now we have learned about electric potential, work done due to moving a charge. Also we have learned about equipotential surfaces. So we'll continue that discussion about equipotential surfaces on this lecture, and also we'll learn about electric dipoles. What are electric dipoles and what is the potential due to electric dipole, what is the electric field due to an electric dipole, and lots of other things. But before that, I wanted to go back to this question that I gave you as homework, right? This question I gave as homework. This part B, right? We had to calculate the work done in moving a 10 microcoulomb charge from point A to point B. Okay, so there are two ways to go about it. One is simple formula, that is work done is equals to negative of Q integration from A to B E dot dl. You can do that. Okay, so if we solve using that, we already have found out the expression for E, right? So if I just place it here, I can compute that. Now here, one difficulty you will get to is that how do you identify the path? Through which path should you go? Because here all of them are varying, so it becomes a bit difficult to compute the integral in one shot. So what we can do is break the path. So our path is from A to B, C, right? Like this, through a path C. So what I will do, first I will choose a path C1. With that, what I will do is I will just change my R. As I am in spherical coordinate system, I will only talk about spherical coordinates. I will change my R. Okay, so not here. I will change my R. So in C1, only R is changing, nothing else is changing, right? So here my d theta and d phi becomes 0. How does it help? It helps immensely because these components go 0 and only I have to compute the integration of E dot AR dot, right? So all these other components are 0, only this component is there, and I will compute the integration only with respect to this component for path C1. Similarly for path C2, R will remain same, my theta will change and phi also will be same. Same for C3, my R will remain same, theta will remain same, my phi will change now. Okay, so I will just compute the work done due to individual paths and add those up. Now this is a lengthy process, I do agree. Obviously in method 2 it will be much simpler. I will show you method 2 as well. Okay, so here work done due to path 1, work done due to path 2, you can easily see, like, don't forget this particular R, right? Don't forget, whenever you're computing, you are doing that dot product of dl vector and your E vector, and dl vector with d theta you have R. So many students miss out this R. Please don't miss out this R. This is a silly mistake that many students do while computing the integration in other coordinate systems like spherical and cylindrical coordinate systems. Same for C3, and you add all of these three up and you get 28.125 microjoules. You just put the values and you get that value. Okay, obviously this integration is a bit difficult, but like once you get the hang of it, right, you will be able to do it. But what's the simpler analysis? What's the simpler way to do this? So if I know electric potential, they have given me electric potential formula with as a function of R and theta and phi. If I know the electric potential, don't I know the work done? Because potential and work done are just related with respect to a charge, right? Test charge. So if I just divide this, if I just multiply this with my potential, I will get my work done, right? So exactly that is what I will do. So what is the formula for work done in terms of potential? It is basically work done AB equals to Q times VAB. The potential change from A to B multiplied by the charge will give me the work done. That was the basic definition of electric potential, if you remember the static definition. So just VB minus VA, if I do and multiply it with by charge, I will get my answer. And what is B point? Like I am doing final minus initial, right? Final minus initial. So what is my charge is 10 micro, and this is potential at the final point, that is B point. I will put my R value equals to 4, theta value equals to 90, and phi value equals to 60. And same for A as well. I will put my R, theta, phi values. I will get my work done. And like simply the answer will come out to be same as the previous case, but this is much easier and less stressful. Okay, and you will this will take you 30 seconds and that will take you 4 minutes. Okay, that even more than that, because it took me more time, because to compute that perfectly, because 100 there is 99% chance you will make some mistake while doing the calculation, right? You will miss some r, you will miss some sine phi, something like that. Okay, so that's how you solve these type of questions. So I hope you understand, and I hope you understood the electric field as a gradient of potential and the concept of equipotential surface. Okay, so now in today's lecture we'll continue with the discussion of equipotential surface, and we'll do a few numericals on equipotential surface, and we'll learn about electric dipoles. So if I have a surface V as a function of xyz which is constant, or V as a function of rho phi z, or which is constant, or V as a function of r theta phi as which is constant, that means all these are equipotential surface. Okay, all these are equipotential surface. So if I write a function, scalar function phi, that is equals to V minus C, if I find out the gradient of that will be normal vector to phi equals to 0. Okay, that is V equals to C curve in the direction where phi is increasing or V is greater than C. Okay, where V increases, simply V increases. Now what is the electric field? This already we have discussed, right? Now previously I was discussing about 0. Now I have put a constant here. So what will be the direction of electric field? Again the same relation, that same as the direction of gradient. Okay, normal vector to phi equals to 0 surface, or V equal to C surface. Normal vector to this V equals to C surface, and in the direction in which my V decreases. Okay, because here there is a negative sign. If this is positive, then this will be opposite of that. There will be negative sign. Okay, so let's read more about equipotential surface. So a bit of information they have given me. Electrostatic fields are always perpendicular to equipotential surfaces. So this is a very important point that you have to note, that your electrostatic fields, right, will always be perpendicular to equipotential surfaces. Why? If the surface is equipotential, I already told, right, the direction of the electric field will be a normal vector in the direction in which V is increasing. So it will be always normal vector. So if it is normal vector, that means it will be perpendicular, correct? So that is a simple reason, right? Because this surface is what? Some V equals to C constant, right? That is what I defined here. So this surface is some V equals to C constant, like the voltage is constant. Equipotential means what? Potential is not changing, voltage is constant. It does not mean potential is 0. It means potential is constant. So I have already established here that the direction of the electric field will always be perpendicular to the plane where potential is constant. Okay, direction later on we can discuss, but it will be perpendicular, and exactly this is the conclusion of that particular point. So electrostatic fields will always be perpendicular to equipotential surface, just like here. If I have a sphere, that's why we choose a sphere, right, as an imaginary Gaussian surface. Things become so simpler. Okay, so yeah, this means that electric field moves from the regions of higher potential to regions of lower potential. So what does it mean here? Maintaining a right angle with the equipotential surface. So like I told you, right, this is in the direction where V decreases. So this surface will have more potential than this surface, because electric field will move in the direction from higher potential to lower potential, as mentioned here, right? So I can I can write in summary, electric field direction of electric field will be from higher potential to lower potential. Potential to lower potential. Okay, so exactly that is what is written over here in summary. So whatever the previous point was, it is just concluding everything. In uniform electric field, the equipotential surface are a series of parallel planes that are perpendicular to the electric field line. So this is a uniform electric field area. So if there is a uniform electric field, so the equipotential surface will just be simple planes, right, that whose area vector are parallel to the electric field. The net work done in moving a charge on same equipotential surface is 0. On same, this point is very important, on same equipotential surface, right? What do I mean by same? So this is one equipotential surface, right? Surface S1. So wherever I move my charge, let's say this is point A and this is point B and this is point C and this is surface S2, correct? So my work done due to AB will be 0. Why? Because work done, just we have learned this, that work done is equals to Q times VAV. And I am just telling you that this is an equipotential surface. If this is an equipotential surface, then VA is equals to VB. That means the potential difference is 0. That means this will be simply 0. But what about WAC? If I am moving from this A to B, these two are also equipotential surfaces, right? Will it be 0? No, right? It will not be 0. Why it will not be 0? Because remember, here there is some potential. Let's name this as VS1. And there will be some potential VS2. These two are not equal. Although whatever potential this surface has are same, whatever potential this surface has are same. But these two potentials are not equal because I just mentioned electric field will be in that direction where potential reduces. Okay? Potential reduces. So obviously, from if I move my charge to here, there is some potential difference, VAC. So in this direction, if I move, my potential will increase, right? Because this direction means potential reduces. So obviously, it will be VC minus VA. As potential has increased, so there will be positive work done. Okay, so I hope you got the point. Now let's do a good question on this. Where this question came on GATE 2016. Try to solve this question and then watch my solutions. So here we have two electric charges Q and minus Q are placed at 0, 0 and 6, 0 on the XY plane. So we are only talking about the XY plane. So if I have X and Y, and at 0, 0 I have a charge of Q, and at 6, 0 right here I have a charge of minus 2Q. Okay, so can we solve this by option elimination? So if I choose this option, right, X equals to 2. So if X is equals to 2, that means minus 2, sorry, it's somewhere around here. Not this, it should be somewhere around here. Okay, so here it is telling me that it is a equipotential curve. Is this correct? If I find out potential here, the distance is something else and the distance is something else, and it will always keep on changing and always depend on R, right? So like at infinity, the potential will be 0 because R is infinity, but near about here, if I find out what is the potential here, so if at infinity the potential is 0, here also the potential should be 0. So it is falling like this, right? It is falling like this. So the potential should be same everywhere, right? Potential should be same everywhere. Is the potential 0 here? We'll check. So if I check this, so this is, what is the distance between them? The distance between them is 6, correct? And this distance is 2. So this will be simply KQ by R square 2 square plus minus, sorry, not R square, sorry, KQ by R minus 2 KQ by R is, this is 8, right? So this is KQ by 4, which is not 0, okay, which is not equal to 0. So option A is gone. Option A is gone simply. Okay, so obviously we can solve this by normal method as well, but still we're trying with options. So what about option B? What about the option B? If I choose option B, it is telling me y equals to 2. So y equals to 2 is this, right? It will be again similar, infinity, this is 0, 2 and here I have minus 2q, here I have q, correct? So if I know this distance, right, what is this distance? This distance is 2, and what is this distance actually? This distance is 2 square plus 4 square, right? Here this distance is, sorry, not 2, 6. So again this is not 0 actually. If you find out, this is KQ by 2 minus 2kq by 2 square plus 6 square 1 by 2. So this is not 0, right? This is not 0. So again, this is not a equipotential surface. So we are only left with this and this, correct? So here actually one interesting point, this is a equation of a circle. This is a equation of a circle, x square plus y square equals to 2. So if I just draw the equation of a circle, I am taking so much time, but you should not take so much time to eliminate the options. So I will draw the xy plane like this, more easier this way, x, y. So this will be here, this is the x square equals to y equals to what is this, 2. So this distance will be under root 2. Correct, this will be 0 comma under root 2. This distance will be under root 2 comma 0. So my charges are placed here, q, and this is somewhere around here, very far away actually, minus 2q, right? And the distance between them is 6, correct? Yeah, this is 6 comma 0. Now can I compute the potential here? Yes, right, I can compute the potential. So what does the potential come out to be? Potential come out to be kq at this point, like if this is a equipotential curve, right? Potential here and potential here, these points should be same, okay? VA and VB, these points potential should be same. So what is VA? Just I'm computing with respect to infinity, with respect to a reference. So here my VA is kq by, not VA, sorry, VB, kq by this distance, so that is under root 2, and minus 2 kq. What is the distance? 6 minus under root 2, right? What about VA? Now this is something opposite actually. So here what is happening, this distance is what, kq, and this is actually, this distance is again under root 2, right? This distance is, this is minus under root 2 comma 0. Okay, so this will be kq by under root 2 and minus 2kq by, this is 6, this overall 6, and plus under root 2, right? Plus 6 under root 2. Again, VA is not equals to VB, so it is again not a equipotential curve. What about the last part? Obviously the last option will be correct. So just sorry for the noise actually, due to my throat. I am having a fever, but still I have to record, we can't stop. So this will be x and y. Now the last equation of circle, right? This is x plus 2 whole square plus y square plus 16. So this is 4 square. So x plus 2 whole square plus y square equals to 16, or I can say 4 square. So this is circle with center minus 2 comma 0 and radius 2. So circle with center minus 2 comma 0 and radius of 2. So it will be just like this, touching here, right? So radius of 4, sorry. If the radius is 4, right? So it will not touch here actually. If the radius is 4, so it will just be like this actually. Pretty big actually. I can make the minus 2 0 much nearer. Okay, so radius, so this will be 2 and this will be 4. Yeah, so this again radius is 4, so this point will be actually minus 6 comma 0 and this point will be 4 comma 0, right? If I'm not mistaken, plus 4 if I do 2 comma 0. 2,0, yeah. And my charge is somewhere around here, minus 2q and plus q. Now things are interesting here, okay. So what is happening here is that let's find out again A and B points. What is VA? VA is due to the first charge kq by what is the distance? 6, right? It is, this distance is 6 minus 2kq. What is the distance? This distance is total, like this is total 6 and again this is 6, so this will be 12. Okay, so this comes out to be 0. What about VB? VB is kq upon this distance. What is this distance? This is 4, right? This distance is 4, kq by 4. And okay, this is actually not due to this charge. Due to this charge it will be kq by 2, sorry. Due to the q charge this will be kq by 2, and due to this charge it will be kq by 4, because this point is at 6, 0, right? kq by 4, correct. Sorry, this is 2 kq by 4, so this will come out to be 0. So here I can observe that VA is equals to VB, so obviously this surface is equipotential because my VAB equals to 0. Now in what other way you can solve? There is one simpler way to solve, because if you read the question carefully, what they have mentioned, two electric charges q and minus 2q are placed at 0, 0, 6, 0 in the xy plane. The equation of the zero equipotential curve, the equation of the zero equipotential curve, if it is talking about zero equipotential curve, that means VPQ will be 0. That is correct. VPQ will be 0. That is correct. But VP equals to VQ will also be equals to 0, because it is talking about the zero equipotential curve. So things become so much simpler now. So what I will do, I will just choose a point. So I told you two methods. This first method is when they are not talking about zero equipotential method, they are talking about any arbitrary curve is equipotential. You can check it like that, okay, with the help of options. But if some hint is given, then things become so much simpler, right? So here I have a q charge and I have a minus q charge, correct? And any point p equals to x comma y I have, okay. So this is in the I will assume this is in the first quadrant and this distance is 6, correct? So I can easily find out the potential at point P, and that should be, I will equate that equal to 0. So potential at point P will simply be equals to, due to the first charge, it will be kq by the distance, right? What is the distance? It is x square plus y square under root x square plus y square under root minus 2kq. And what is the distance here actually? So x has reduced by distance 6. So I will assume that x is greater than 0 and y greater than 0. That is my assumption. So this will be x minus 6 whole square, as I am lying in the first quadrant, correct? And plus y hasn't changed, y whole square whole under root. This should be equals to 0. So if this is equals to 0, what will happen? So overall here this will come out to be x minus 6 whole square plus y whole square. Now if I square on both sides, if I just square on both sides, what will happen? Take that there, this will be 4x square plus 4y square, and this will come out to be x square plus 36 minus 12x, and this if I just, this is 4x square plus 3y square. So this will also become 3y square. So like if I just write this down here, 36 will remain here, 3x square plus 3y square and plus 12x equals to 36. I will divide everything by 3. So this will be x square plus y square plus 4x equals to 12. So what do I need? I need to make this a square, right? So what I will do, x plus 2 whole square, correct? X plus 2 whole square. So what extra I have added? I have added extra 4, right? And then I have to subtract 4 as well. That 4 will go on the right hand side. This will be y square equals to 16. So this is the equation basically. This is the equation, this is the answer, correct? So option C will be correct. D will be correct. So I have mentioned both the methods using basic option checking, and obviously using this hint they have given that your surface is zero potential, right? So you have to understand that what are they talking about. So in summary, one important point about this is valid for the point charge as well, that electric field will be zero inside and electric field will be outside will be simply kq by r square AR cap in the air cap direction. Potential inside will be constant. Okay, it will be constant, it will not change. That is, it will be kq by r, whatever the potential at the surface. Okay, and potential outside will be simply kq by small r. Okay, that's just formula we have used. And for solid perfect conductor, this concept we will use later on, so please keep this in mind. This will we will use again. Electric field inside will be zero, electric field outside will be kq by r square, same as the hollow. So hollow conductor, same potential also will be same. Potential will be inside kq by capital R and outside will be kq by small r for a solid conductor, perfect conductor, solid perfect conductor. But for a solid conductor which is not perfect or a non-conductor, charge can be equally distributed. Okay, it can be distributed and it can be inside the surface. Then the formula becomes kq by capital R by r cube, and if it is outside, same as the point solid conductor. Okay, and inside the formula will change, outside it will remain same. You can derive or you can remember, whichever you wish to, like whichever you choose to. Okay, so summary, like here I've given the behavior of a perfect solid conductor, which we have revised multiple times. This again will come, right? This after few lectures, this will again come. The behavior of a perfect solid conductor is identical to that of a hollow conductor. The potential is the same at surface and inside the volume of the perfect conductor. The surface of a perfect conductor is an equipotential surface. The volume of a perfect conductor is an equipotential volume, meaning there is no potential difference inside. Okay, so that's why we take the Gaussian surface as such. We take the Gaussian surface, which is a equipotential surface. The electric field is always perpendicular to the surface of a perfect conductor and points in the direction where the potential decreases. Basically, it's like a point charge. Simply you assume a solid conductor, perfect conductor as a point charge. Okay, that's it. Everything resides on the surface and electric field is radially outwards. Okay, so now we'll study about electric dipoles. So what are electric dipoles? Basically, electric dipoles are nothing but two charges which are equal and opposite to each other and placed very near. An electric dipole consists of two equal and opposite charges separated by a very small distance but bound together. You can assume it like an hydrogen atom. In a hydrogen atom, we have like positive charge here, right? Proton, which is inside, and a single electron that always revolves around it. Correct? If you remember chemistry, if it is in your memory, so a negative charge actually revolves around it, right? So you can take the example of a hydrogen atom. So electric dipoles are nothing but two charges of opposite sign but equal magnitude and bounded together. The dipole moment is defined as q times d, charge multiplied by the distance, separation distance. It is in vectorical format, also known as p equals to q times 2l. Now why suddenly all of a sudden we are talking about moment? What is the reason? We will understand that once we derive few expressions, we will understand why we are talking about moment. But just for a second, now we understand that the dipole moment, right, will be simply charge multiplied by the distance between them. Okay, just you have to keep in mind this expression about dipole moment. What is a dipole moment? The magnitude of the charge times the distance between them. And if you want to talk about in vector format, it will be q into 2l vector, right? Q into 2l vector, simply like that. Whatever the direction of L is, that is the direction of the dipole moment. Just do keep this in mind. What is the direction of L? Direction of L vector will be from negative to positive charge. Direction of L vector will be from negative to positive charge, basically opposite to the electric field, because electric field radiates from positive and terminates at negative. Just the opposite, right? Opposite of electric field, it will be from negative to positive. So you have to keep in mind two things. One is dipole moment is equals to q into 2l vector. Another one is direction of L vector will be from negative to positive. These two things you have to keep in mind. Why? I will explain just in a minute. Okay. And one more important point is that as they are bounded together, right, they are very tightly bounded, I cannot simply separate these two charges. I cannot easily separate these two charges. They are very tightly bounded, so none of the charge can move independently. If I move this plus q charge, along with it minus q also will move. Okay, so that is a property of a dipole. Now let's find out the electric field caused due to a dipole. So there will be two types of electric field. First, we'll derive the axial electric field, or also known as along the axis of the dipole. Axis of dipole, or perpendicular to dipole, right? Or perpendicular to dipole. Not perpendicular. So along the axis is this, right? This is the axial line along the length vector. Okay. So along this direction, what will be the electric field? Because there will be some electric field in two directions this time. This direction and obviously in the perpendicular directions. We'll understand that. First of all, let's find out the electric field here at this point. Okay. We'll derive for all the expressions. Don't worry. So electric field here. Can I simply find out the electric field? Yes, it is pretty simple, right? Because here I have 2 point charges and I have to find out the electric field at this point, and I know the simple electric field formula due to point charges. Just hold on. Yeah, the simple electric field formula is what? Electric field. So due to this plus q, right, I will get a electric field along this direction, E plus, and due to this minus q, I will get a electric field along this direction. Correct? So I have already taken sign into effect, so I will not write the charge with signs. Okay, I've already taken the sign into effect. So my E will be E axial. Okay, E axial, or I can say E in the same axis will be E plus minus magnitude of E minus. I've already taken the direction into account. Okay, so like this, the direction I can write also as the direction of AL cap, right? The direction of the length vector. So what is AL cap? AL cap is simply L vector upon magnitude of length. That's it. Okay, so you can write it like this, the electric field. So this will be simply, if I derive this, what will be E plus? E plus magnitude will be what? I'm just talking about the magnitude now. Direction has already been taken care of. It will be kq by r square. Kq. Let's assume that the distance of this particular point P, right? This is the point P. Like here, I'm talking about here only, point P. It is this distance from the center of the two dipoles is r. So what will be the distance due to this plus q? It will be small r minus L. So it will be r minus L whole square minus, this is the E plus, right? And magnitude of E minus is equals to kq divided by r plus L whole square. If you observe here carefully, this extra L, and obviously this total distance is r. So overall, my electric field will be this, right? Kq by r minus L whole square minus kq by r plus L whole square. I can simplify this thing. This will be kq will be common. This will be r plus L minus r minus L. So it will be something like this. 2r and 2l divided by r minus L whole square into r plus L whole square. Okay, so something like this will come up, right? If I'm not wrong. So here what I can do is that I can assume one thing. What we can do is, what is this? If I write this in whole brackets, right, r minus L into r plus L whole square. So this will be equals to simplification kq 4rl divided by r square minus L square whole square. Okay, if I simplify this further, I'm not talking about the direction for now. So I will assume something. I will assume that what I will assume? I will assume just to approximate to get a good result is R very greater than L, right? So the distance between these two dipoles is anyways very smaller. The distance at which I will measure the electric field will be very further away from as compared to this 2L distance. So we'll assume R very greater than L. So this L square I can ignore. Okay. So what will this overall simplify? So this thing will be simplified to electric field in the parallel direction. This is in the parallel direction, right? This is equals to KQ by 4L divided by R. So one interesting thing here happens is that this is AL cap, right? AL cap. What is the interesting thing? The interesting thing is this L into AL cap is actually L vector, correct? And 2Q into L vector is what? 2Q into L vector is what? Simple dipole moment. So that's why we just write this in like it's neat in that way that this gets simplified to 2KP divided by R. My electric field along the axis of a dipole is simply this, okay, where my P is simply Q times 2L AL cap direction, correct, where AL cap direction is from negative charge to positive charge. So this you can remember, okay, this is the actual electric field. Now let us actually derive the equatorial point or the perpendicular bisector electric field, right? So because there will be some electric field here, okay, there will be some electric field perpendicular to this, like in the y direction basically. So how do we compute that? So if I take a point here, right, in the midpoint from this dipole, if I take a point here, I will observe that the distance from the point is R here. So this minus Q will have electric field on this direction and this plus Q will have electric field on this direction. So the sine theta component, right, gets cancelled due to plus Q and minus Q due to symmetry. The cos theta component is only present. So I will just compute the cos theta component. So first of all, what is the electric field due to this minus Q and plus Q? So electric field due to plus Q is simply, I am talking about magnitude now, is simply KQ divided by R square. Here R is simply H, right? The distance is H, and I know what is H. H is basically R square plus small l square. So H square, and electric field due to the magnitude of electric field due to the negative charge is again same only. Magnitude will be same, direction will differ, but this will be same, right? Overall, I will have electric field in this direction, that is 2E cos theta. So it will become total electric field will be. So basically I am just computing the electric field along the axial line. Along the axial line, what will be the electric field? Along the axial line, the electric field will be this, okay? Electric field will be this, okay? Along the axial line, the electric field will be this. Axial electric field along the axis of the dipole, the electric field will be this. On the perpendicular bisector, I can only compute on the perpendicular bisector, not here. It will be difficult for me to compute here, okay? But along the perpendicular bisector of the dipole, the electric field will be simply this, right? It will be, so overall my electric field along the perpendicular bisector magnitude will be 2KQ cos theta. What is cos theta? Cos theta is base upon hypotenuse, L upon H. So it will be 2KQL upon H cube, okay? So I can further rewrite this, okay, in simple expression. What I can write this something like this. It will be magnitude of EL will be 2KQL divided by R square plus L square 3/2, right? Because H is under root, so 1/2 power comes up. So now what do? I do this. This direction will be in the opposite direction to the DL vector, right? Because DL is from minus Q to plus Q. So my E perpendicular vector, right, direction along the perpendicular bisector. Now remember this 2QL is what? Again, dipole moment. So I can write minus K P divided by R square plus L square 3/2, where R is the perpendicular distance from dipole, midpoint of dipole. Okay, so this you have to remember. The direction is very important, right? Here the direction is very important. Please remember the direction. Okay, please, this is very important. I will highlight this. Okay, actually I can further simplify this, right? If my assumption is R is very greater than L, so actually I can further simplify this expression. So this will become only RQ, right? Only RQ will be present over here. Okay, only RQ will be present over here. So this is the equatorial like electric field, and this is the axial electric field, right? And just remember this thing, that equatorial electric field will be in the opposite direction. Okay, so now if you want to find out the electric field at any point P, random point P, which is at R0 distance, okay, from the we can assume from the center, right, which is at R0 distance from the center, correct? So this distance is R0. And from here to here the length is L. This is not to scale, okay, not to scale, please excuse my drawing. So there are two methods to solve this. One is using general method. What is general method? Simply write the electric field in vector expression due to a point charge. We know how to compute the electric field at a point due to a point charge. You will compute due to this, you will compute due to this, then apply vectorically, add these two, then apply approximation that R will be very greater than L, and you will get your answer. Okay, but if you don't want to do that, okay, if you don't want to do that, you can use a shortcut. But if you are not able to understand the shortcut, you have to go use the generalized method. So first method is use general method of electric field due to point charge. Okay, now what I can do is, actually one trick I can do is I can break this down, like this vector moment, right, this dipole moment, I can break this down into two components. As this is making theta angle with respect to, like this point is making theta angle with respect to my dipole moment, I can break it down into two components, resolved into two components. One will be along the axis, another one will be perpendicular to the axis, right? So due to this dipole moment, right, it will like this point will exhibit a axial electric field. Due to this P2 dipole moment, this point will exhibit a equatorial electric field, and equatorial electric field will be anti-parallel to the P2 dipole moment. So I can exactly do that, correct? I can do that. So what will happen is P1, now remember, as I am resolving this P in terms of P1 and P2, so obviously the magnitudes will also reduce. So what I can write here is the E1 vector, right? E1 vector will be what? E1, magnitude of E1. This distance is R0, right? Or R, I can say. E1 will be simply axial. What is axial? It is 2 Kp magnitude of cos theta, because now obviously the P1 is P cos theta, right? Divided by simple R. What is E2 magnitude? E2 magnitude will be Kp magnitude sin theta by r cube, and obviously there was another expression. Okay, something okay, L was there. Is it? No, L is not there. Fine, L is not there. Here I think L was there, right? If I remember correctly. Yeah. Actually, I messed up here. This should be r cube actually here. I messed up. This should not be r only, because this r whole to the power 2, r square whole to the power 2 is 4, and r gets cancelled. So this becomes r cube. Sorry for that. So here actually this is r cube. Okay. This thing is r cube. Correct. So now what we can do is we can simplify this. Okay. What we can do is this thing, right? My net electric field will be what? Magnitude of the net electric field will simply be the square and under root of both of this, right? So it will be simply magnitude of P will be outside, K will be outside, R cube will be outside, and inside I will have 4 cos square, or if it is 4 cos square theta plus sin square theta, right? So it will actually become 3 cos square theta plus 1 whole under root. Okay, so this will be your magnitude of potential, not potential, electric field. This will be the magnitude of electric field. Now what about the direction? So if you observe, if I am identifying this in the spherical coordinate, this direction is in the a theta cap direction, and this direction is radially outward. This is in the a r cap direction. So this will be actually, if I just remove the magnitudes, this will be in the a r cap direction, and this will be in the a theta cap direction. Whatever the direction of theta is, that will be the direction, right? A theta cap direction. Okay. If I am talking about in the spherical coordinate. Okay. So now you can resolve these two coordinates and find out. Or if you don't want to find it out like this, if you want to find it out in rectangular coordinate, you can simply find it out using the generalized expression. Either way suffices. Okay. Now we'll start with force on a dipole due to in an electric field, in an external electric field, due to an external electric field, right? Assume electric field E is directed to the right. Okay, it is directed towards the right of a dipole. The forces on the positive and negative charges of the dipole will be F plus F minus will be equals to QE. Okay, the magnitude will be same, right? Just they will be in the opposite direction, because if electric field is like this, then due on this minus Q charge, it will go on the left hand side. Force will be on the left hand side, right? Due to on this plus Q charge, force will be on the right hand side. But sir, you just told that dipoles are tightly bounded together, they can never separate, they are trying to separate. No, if you look at overall as a system, the force, right, is 0. F net is 0. Overall as a system of these two particles, I have some F plus here, F minus here, both are cancelling each other out. So F net in the rectilinear direction is 0. So although there is no linear motion, but the dipole experiences torque. The dipole actually will experience a torque. How will it experience a torque? Because it is experiencing a force here. Okay, what is happening if I break this force down into two components? Let's assume this as theta. So here is one component and here is the other component. Resolve this force, and again, just like our JE days, right? We used to resolve the force into components. This is again theta, correct? This will be some component and this will be some component. So now if I observe that this force will be equal, actually they will cancel each other out, but this force, what is happening, this is giving it a rotational motion. So there will be some rotational motion. So due to this force about the center, this force will create some torque, and this force will create some torque. The magnitude will be equal, the direction are opposite, so there will be some circular motion. Okay, so what is the magnitude of the torque? Let's assume the force is F, right? If the force is F, so torque on this here, right? Let's assume this torque is tau 1 and this torque is tau 2. So my tau 1 is equals to what? Tau 1 is equals to tau 2, magnitude of tau 1, tau 2 are is equals to F magnitude, okay, into distance T by 2, right? And obviously don't forget, we have actually resolved this force. This force is not F, right? If this is theta, this force along the axis will be F cos theta, and this force will be F sin theta. So I have to write this magnitude of the F into sine theta, right? Force has been resolved now. Sine theta into d by 2. Just hold on. So this will be F sine theta, and overall two torques are acting in opposite direction. So torque net magnitude will be, I will add these two up. So overall this will become magnitude of F into D into sine theta. Now can I write this in more simpler manner? Actually I can write this in more simpler manner. How can I write this in more simpler manner? So here, right, if you want to write this in terms of direction as well, what is happening is that I am actually doing a cross product. Okay, cross product of what? Of this dipole moment and this electric field. Because if I take the cross P cross E, I will get magnitude of P, magnitude of E, sine theta. If I am just purely talking about magnitude. So what is magnitude of E? Magnitude of E is equals to F upon Q, right? Magnitude of E is F upon Q. So F upon Q, and what is P? P is if you remember, P is equals to Q times the distance between these two, right? Q times the distance between these two. I should actually maintain consistency here. This should actually be L. Okay, this should actually be if this is, let's write somewhere that my D is equals to 2L. So this I can write. I will write at the next page. I will write here only. This I can copy. So here, what will happen here is, as D is equals to 2L, so my torque net magnitude is equals to this, right? F I can write as what? F I can write as Q E, correct? Q E times 2L sine theta. So what is this basically? What is this? So Q E is one separate quantity. Q into 2L is dipole moment. And if I'm talking about direction, torque net will be dipole moment cross my E vector. Okay, so like that's why we care about dipole moment so much, because all the results that are derived using of a dipole, right, is derived with the help of a dipole moment. Okay, dipole moment expression is getting everywhere, so it's easier for us to remember. Okay, but direction matters here. This torque will be in this direction because I'm rotating like this. Electric field is in this direction, so I'm rotating like this. First, what is happening? L cross E, because it will rotate in this direction. It will not rotate in this direction. Why it will rotate in this direction? Because electric field is in the right hand side, and plus Q charge will also move on the right hand side. Why? Because due to this plus Q charge, right, what happens? Electric field is in this direction, so assume that there is some positive charge at the left hand side. From that, some electric field is originating, so this charge will get repelled from this. So electric field will move on the right hand side, and due to this positive charge, this charge will get attracted simply. Okay, so you can assume it like that. So I hope you understand the concept. These are all basic concepts. We are not going too much into the depth of this. Okay, just need to understand the basic things and just go through by yourself. You yourself will be able to derive all this. Now let's solve a question. When an electric dipole P moment is placed in an uniform electric field, at what angle between P and E the torque will be maximum? Can you tell me at what angle the torque will be maximum? So what is the expression for torque? The expression for torque is magnitude of the torque is this, right? Magnitude of the torque is torque net is magnitude of the P, magnitude of the E, sine theta. So I can safely say that if my theta is 90 degrees, dipole moment will be maximum, because all these are constant. So is there any visualization here? So if my positive charge is lying here, right, and field is also in this direction, so it will get full force. It will get the full force, and it will totally rotate until what? Until equilibrium is reached. What is equilibrium? Until it is totally parallel. Okay, sorry. Until my dipole moment is parallel to the electric field, it will keep on rotating. Is there another value of theta? There is another value of theta. Theta equals to 270 degree. So if my theta is equals to 270 degree, that also is possible, right? If theta is here, I am somewhere around here, positive charge is somewhere around here, then what will happen? Again, dipole moment will work in this direction, right? Dipole moment will work in this direction, and it will reach in equilibrium position. So what will happen is, so torque will keep acting on the dipole until the dipole moment is parallel or anti-parallel to electric field. Okay, so it will reach equilibrium when dipole is parallel or anti-parallel to electric field. Now in a certain region of space, the electric field is oriented along z direction. Okay, fine. However, its magnitude is not constant. Okay, it increases uniformly in positive z direction at the rate of 10 raised to power 5 volt per meter square. So basically what they are telling me, that electric field is only along the z direction, and it increases, it is only along the z direction, and it is a function of z. It increases linearly with 10 raised to power 5, right? So this is the expression that they are talking about, 10 raised to power 5 volt per meter square. Fine. What are the force and torque experienced by system with a total dipole moment of 10 raised to power minus 7 centimeter meter directed in the negative z direction? So if I have a simply dipole moment that is placed where with the total dipole moment is this and directed towards negative. Okay, so I have a dipole, okay, which is by a system with a total dipole moment of this. So I will assume like something like this. So electric field is let's say this is the positive z direction, right? So electric field is in this direction, and dipole they are telling me is in the negative z direction, right? And its magnitude is 10 raised to power minus 7. Let's assume dipole to be any place, right? Any place here. Let's assume this minus q and plus q, and it is directed sorry, minus q should be here and plus q should be here, directed like this, and the distance between them is d. Okay, but I know the electric field in this will be what? Electric field will be simply this, right? Electric field, if I just derive this expression, electric field will be 10 raised to power 5 z az cap, correct? So this will be the electric field. Now here, if I have to compute the total force on this, what will be the total force? So the total force here and total force here will be what? So the total force on the positive fz, right? Let's assume that this is some place at like any x, y and z, right? Let's assume this as anything you can assume. I will assume this as 0, 0, z. It doesn't matter, xy coordinate doesn't matter because it will always be perpendicular. So electric field will always be along the z axis, and this will be what then? This will be 0, 0, z minus d. Okay, this will be 0, 0, z minus d, right? Whichever is suitable to you. So f plus will be simply 10 raised to power 5 z into q, correct? And f minus will be in just the opposite direction. Okay, I am just talking about magnitudes now. It will be 10 raised to power 5 z minus d q. So what will happen? Overall force on the system F net will be what? It will be like, due to this the force will be on this direction, and due to this the force will be on this direction, correct? This will be the direction of the forces So what I can say is, if I have to subtract the forces, correct? So it will be F plus, I will assume positive z direction, F plus minus F minus. So z actually the unknown thing gets cancelled. So it becomes very simple. This becomes 10 raised to power 5 into d into q. Okay. And what is dq actually? dq is actually the magnitude of the dipole moment. So this becomes 10 raised to power 5 into magnitude of the dipole moment, 10 raised to power minus 7 coulomb meter, right? This is coulomb meter and this is volt per meter square. So everything is in SI units. So this will simply come out to be 10 raised to power minus 2 Newton. So this is a very good question. Actually, the unknown z actually vanishes. Okay, it is independent of the z. Okay, it does not depend in which direction I am at. Okay. Now what about can you find out the torque of this? Can you tell me what will be the torque? So here, what is the expression for torque? The expression for torque was dipole moment cross E. And what is the angle? So here, dipole moment is also in the z direction, right? They are talking in dipole moment is also in the negative z direction. So if it is in the negative z direction, obviously it is on the z it is on along the line z axis only. So xy can be present, but what I can say is it will be magnitude of P magnitude of E sine theta. So if this direction is along the negative z direction and this E direction is along positive z, so theta is actually 180. Now if theta is 180, so this torque will be simply 0. So there will be no net torque here, there will be force, there will be a net force, this, and which is a constant force. Okay, so the particle will actually keep on accelerating at the top and okay, particle will keep on accelerating. Now there are three charges, 2q minus q minus q, are placed at corners of ABC of an equilateral triangle with side length A, as shown in the adjoining figure. What is the dipole moment of this arrangement? So by dipole moment, what are they telling? Okay, how do I find out the dipole moment? So actually what is happening, I can actually break this arrangement down into two arrangements. Okay, so I have a minus q here and plus minus q here, right? So I can break this charge to plus q plus q. Basically what is happening, this is 1 plus q and this is another plus q. Okay, so this will be minus q and plus q, right? So basically I can break, like I can find the dipole moment due to this, I can find the dipole moment due to this and add these two up, and that will be my overall dipole moment. Is this correct? No. Actually, what is the dipole moment? Dipole moment is from negative to positive. So here this is causing some dipole moment P1 and this is causing some dipole moment P2. Okay, so overall dipole moment will be what? Actually due to this, right, I will resolve this component. It will have some left component, top component. Again this will have some right, top component. So overall dipole moment will be here. Okay, so actually what is this angle? So this angle first of all is theta, that is 60. This is a equilateral triangle, this angle will be 60. So if this angle is 60, right, what I can say, my drawing is really bad, I'm sorry for that. So actually this angle, right, this angle also will be 60 and this angle also will be 60. Okay, so if this angle is 60, so again I can break this down. So overall my dipole moment will be what? Magnitude of P1 sine 60 into 2. Okay, because magnitude of P1 and magnitude of P2 are same. Okay, I can stay here because like they are in like the charges magnitude is same, the distance is same, so obviously everything will be same. Magnitude of P1 will be equals to magnitude of P2. This is my dipole moment P of the equivalent system. Okay, this is not actually representing a dipole moment, but of the equivalent system. If you have to find out the dipole moment, I can write like this, right? Dipole moment of the equivalent system. Okay, I hope you understand. This is just a equivalent system, not actually like dipole moment is present here, right? Just the equivalent system. So what is magnitude of P1? P1 magnitude will be q times the distance, right? Q times the distance is a. Okay, and this I have to write sine 60 is root 3 by 2. So overall my dipole moment P will be root 3 by 2. This will become root 3 only, root 3 QA. This will be my answer. Okay, pretty simple standard question. These questions can come like daily. Dipole is not that much important like gate point of view, but still they can ask questions. Now let us come to potential. What will be the potential due to a dipole? Now things are more simpler here. Okay, if I have to find out the potential due to a dipole, how can I resolve the potential due to a dipole? So what will be this length? This length, right, will be simply r minus L cos theta. Just like this is an approximation. Here this length is L, right? If I take the cos theta of this, so the remaining length will be this length. That is my approximation. Again, this length will be r plus L cos theta. This will be plus, because here what is happening is that if I just draw the EQ like this, if I draw this perpendicular, right, this angle will be 90 minus theta actually. Okay, so this is L, so this, right, this will be L sin theta, L 90 minus theta, that is L cos theta. Okay, so this length, overall length will be r plus L cos theta, and this length will be r minus L sin theta. I'm just this is just an approximation that we have to take. Okay, now if I try to derive the expression for potential at a point P, any random point P, this will be due to the negative and positive charge. I will obviously take the charges sign here, kq by r, due to point charge, that is L minus cos theta, and plus minus kq by r, that is r plus L cos theta. Okay, so overall this becomes, if I take the kq common here, right, r 2r is at the top, and at the bottom this is r square minus L square cos square theta. Correct. Okay, this is minus, right? So actually 2r will not come, 2L cos theta will come. Again my approximation, that as r is very high than L, so this will come out to be simple like 2LQ is again dipole moment. So this is dipole moment, and cos theta will be there, and at the bottom we'll have AR square. Okay, so this will be simply your potential at any random point P due to a dipole. Okay, so you can like remember the derivation, that's it, right? You can remember the derivation, no need to remember the formula. Anyways, dipole is not that important in for syllabus point of view. Now can you tell me, okay, this has already been derived, dipole moment has already been derived. There is can you tell me this question, the electric potential at a point P due to an electric dipole will be this. Now you might say, sir, we haven't derived any like this any expression anywhere, but actually we have. See, if you observe this, okay, like it cannot be a vector, right? These two options are anyways gone. Cannot be a vector. Okay, it cannot be a vector. But what about this? So here this is talking me P dot r cap by r square. P dot r means what? Magnitude of P into magnitude of r by r cos theta by r square. Here we have something like this. Okay, but we don't have magnitude of r at the top. To get a magnitude of r, we have to multiply and divide by magnitude of r on both sides. So option A will be correct. How? Just derive this, right? K into magnitude of P into magnitude of r, that is simply r into cos theta by r cube. So r gets cancelled. So this will become magnitude of P, magnitude of r, magnitude of P cos theta by r square. So this is also another format that you can keep in mind of that. Okay, this is also another format for potential due to a dipole. So with all this, right, we actually end our electric dipole topic discussion. It's a small discussion. This is not that important, but still few things can be asked on this. Okay, so we actually have finished like a part 1 of electrostatics. There is another part that is about different mediums, and of course capacitors. So we'll study about different mediums on the next lecture, and of course after that we'll start with capacitors. Thank you for watching, and I will see you in the next lecture.